This Power America BP5 OIF project is about establishment of WBG Power Electronics Testing Facility for education and workforce training, engaging Power America industry members. The PI of this project is Professor Baran, and the co-PIs are Dr. Wensong Yu, and I am Shubhash Shishparacharya. I am presenting on behalf of my team here. So this project is establishing a comprehensive WBG power electronics testing facility which can be used by all Power America members for doing four main characterization tests: the EMI tests, the high power double pulse tests for different devices, low voltage as well as high voltage silicon carbide devices, and also in the future gallium nitride devices, partial discharge tests, and reliability tests of these devices. The key metrics of the proposed high-powered WBG system testing facility are given out here, where the high-power EMI tester has a voltage level of 800 volts, 200 amps. The double pulse test setup can go up to 10 to 15 kV for different devices with different current ratings. The partial discharge tester can go up to 40 kV, and the reliability tester can go up to 10 kV. And the current levels are dependent on the various tests for avalanche as well as short circuit testing. This slide shows the completed double pulse testing and the test setup for low voltage devices like 800 volts and high current, 200 amps. You can see the test setups, the devices being used, and the measurement systems that are used for the DPT test. This slide shows the DPT for the high voltage devices going up to 10 to 15 kV silicon carbide devices. And a lot of care has to be taken in terms of the packaging of the inductors, in terms of parasitic capacitance, the layout of the circuit to minimize the inductance, and of course the gate driver. And we use an intelligent gate driver so that we can actually study features of the gate driver itself. This slide shows the CAD design that is done prior to the tests for minimizing the inductance, and the placement of the device, and the hot plate for heating up the device to high temperatures for the DPT tests. This slide shows the results for the generation 3 10 kV silicon carbide MOSFET, a single die of 15 amps, the turn on and turn off of these devices at 5 kV DC bus, and 10 amperes. And one can then measure the on-offs of these devices from these kind of tests, and also evaluate the gate driver effectiveness in terms of different gate resistance. Next, we also have a reliability test bench for the avalanche ruggedness of these devices, where these devices are taken to their avalanche voltage, and the avalanche energy rating of these devices are evaluated. So this is a standard UIS test setup, and the test setup looks like this in this particular slide, where we carefully build the inductors in different sections to provide the half Li square energy required for the avalanche tests. Here is a test result for the 10 kV MOSFET, again for the avalanche test, and the avalanche energy of the 10 kV MOSFET is around 7.65 joules at a current of 34 amps and the avalanche time of 27 microseconds. the avalanche voltage of this device is 15.8 kV. So that is substantially higher than the breakdown voltage of the 10 kV MOSFET. So this is basically evaluating the ruggedness of the device. We can actually plot this kind of a ruggedness chart where we can plot it against the current, the avalanche current versus the time required for the avalanche. And in all cases, you see that this particular die has an avalanche rating of more than 7 joules. We have done avalanche testing, or we can do avalanche testing of low voltage as well as high voltage devices. And based on the active area, we can actually plot the avalanche density, energy density in joules per centimeter square for each of these dies. Then the next is that we can do short circuit characterization of these devices, where we can actually provide the rated voltage and intentionally cause a short circuit and measure the short circuit currents. So this is the setup, and then these are the results where we have taken these 10 kV MOSFET dies at different voltages, at different VDC voltages for the short circuit. And you can see these ratings from 500, from 4,000 volts to 5,000 volts to 6,000 volts, and the fault and the short circuit current as well as the short circuit time. At 6 kV, the peak current with a 15 amp die goes to around 240 amps, and the short circuit protection time is around 2.4 microseconds for the gate driver to react and shut it off. The short circuit capability of these devices at 6 kV range somewhere between 5 to 6 microseconds. Another test setup in this project is the EMI test setup for comparison with the EMI standards. And here is a block diagram of the test setup with the LISN and to measuring the EMI for a machine with the DC-DC converter and the DC to AC converter. So this is important because we want to actually measure the impact of the common mode voltage for inverter-driven machines. And this slide shows all the different parasitic capacitances that exist in the machine where the common mode voltage is going to impact with high dV by dt. Here's a quad chart of this particular project where we are setting up these 4 different test setups such that any industry member or anybody can actually avail this facility for doing these tests and characterization. So that's the complete project. And this test setup will be available for all industry members and Power America members, as well as others, to use this facility for doing these particular tests or, for all their devices and to procure data from these tests. Thanks for this presentation. And if any questions, please email us. Thank you.